into Let's Talk Chemistry with Pastor Dan. Now, I'm going to put in a concept here that won't be on the test. And it's just because of the fact that I want some opportunity for you to see it. I used to include this when I taught of about 10 to 15 years ago. They changed the way that we do things here. And I had to cut this out because I just ran out of time. But I wanted it in there so that way you see it and know that it's real and understand how it works. So that way, if you end up going forward with this at some future time, you see it, it's not brand new. So the concept we're looking at are called colligative properties. Colligative properties are properties of solvents that are changed as they become solutions. So in other words, when we go from a solvent to solution, because there's things inside of the solvent, it changes the property and it's not the same as it was before. Now, there are 4 types of colligative properties. We're going to look at the middle 2. The first is called vapor pressure depression. So think about when you're cooking pasta. A lot of time if you put salt in it, it'll boil faster. The reason for that is because when it becomes a solution, it depresses the vapor pressure and it boils more rapidly. The last one is called osmotic pressure. That one has something called Raoult's law. I always like saying that. Raoult's law. Raoult's law has to do with how a solvent goes through semi-permeable membranes, so the process of osmosis. You don't use those necessarily as often in chemistry. The 2 middle ones we use more often. So therefore, those are the 2 that we're going to focus on here. The first is called freezing point depression. The second is point of elevation. Think about antifreeze. When you put antifreeze in your car, you do that so that the temperature is colder than water so that your vehicle doesn't become an ice block. And the boiling point is elevated so that way when you're driving around and it's 85, 90, maybe even 100 degrees, your car's not going to overheat. So those are what we do. So here, let's take a look at the process. The definition of it is the amount of freezing point is lowered as the solvent becomes a solution. Now, the equation we use is delta T sub F. Remember, delta in science means change. So change in the freezing temperature. Kf is a constant. It's called the freezing point depression constant. And then we just got done doing solutions. Remember, molarity, capital M, small m is molality. Now, it's a constant, so the only Kf you need to know for sure they're going to use most often is water, and the Kf of water is 1.86 degrees Celsius per mol. So let's look at a problem here. Calculate the freezing point of 200.0 milliliters of water if 76.22 grams of potassium chloride is dissolved into the solvent. So there's our equation again, delta T sub F is equal to Kf times M, and we're definitely looking for the change. Now, we're not actually looking for a change, we're looking for the freezing point, but we need that to define the freezing point. All right, Kf is 1.86, and again, we know that because it's water. All right, now molality, we're going to have to find the molality. Remember, molality is moles of solid over kilograms of solvent. And my solid here, if you look in the problem, is KCl, potassium chloride. My solvent is water, so it's kilograms. So we're going to find both of those values, plug them in, divide them, and get our answers. So we're going to start with our 76.22 grams KCl. Now, to go from grams to moles, we're always going to use our formula mass over 1, potassium's 39, chlorine's 35.5. We get 74.5 grams is 1 mole. We're going to put the grams on the bottom, moles on top, cross out, unit factor label, dimensional analysis, all those kinds of things. My grams cross out, multiply through. I get 1.25 when I use my handy dandy calculator, and I only have 4 sig figs and 76.22 because that's an equality. It's something significant. That's in my numerator. Now we're going to take my 200.0 milliliters of water, but remember I want kilograms. So first I got to do grams to milliliters. I do that using the density of water. Density is 1. So 1 gram is 1 milliliter. 1 kilogram is 1,000 grams. Divide through, I get 0.2000 kilograms of water. We plug that right in there, and we end up with 5.115 mol. Now, I'm going to put that into our problem with 1.86 times 5.115 mol. We divide through, and we get 9.514 degrees Celsius. Now, that's not the freezing point. That's a change in freezing point. What does water freeze at? Well, in Celsius, it's 0. Okay, and that's infinitely exact 0. And it's depressing, so we're going to subtract. So subtract 9.514, and we get negative 9.514 degrees Celsius. That's our answer. All right. Now, the other one we talked about is boiling point elevation. The amount of the boiling point is raised as the solvent becomes a solution. The equation looks an awful lot like that. That's the reason why I do these two together. Delta B, and again, delta T sub B is a change in boiling temperature, not the actual boiling temperature, but the change. KB is a constant again, and M, same thing as molality. Again, the only thing we have to worry about is the KB of water, which is 0.51 degrees Celsius per molal. All right, so look at the problem like the following. Find the mass of calcium chloride needed to cause water to boil at 113.455 degrees Celsius if you have 500.0 grams of water. Now, I am not asking for freezing temperature. I'm asking for how much I need to make the temperature change. So using my equation again, graphic organizer, we're going to start with this. Now, the change is not 113.455. That's what it is at the end. So what does it usually start at? Well, it starts at 100. So we take the subtraction of the two, and that's our change, 13.455 degrees Celsius. My KB, it's water again, so therefore it's going to be 0.51 degrees Celsius per mol. And my molality, that's what we're going to find out here. So if that's the case, M is equal to delta T sub B over KB. Put our values in. We have the huge molality. Now, that's a concentration. Remember we talked about before. If I'm giving you a concentration, you never start with it. So that means we're going to start with my other value here. We're going to start with 500.0 grams of water. Now, you remember I talked about moles. And solute goes to moles. It's not a solute. Solution goes to liters. It's not a solution. Water is my solvent. Solvent goes to kilograms. So therefore, 1 kilogram is 1,000 grams. And now we're going to use that molality as a unit converter again. Take 26.382 moles of it over 1 kilogram. My kilograms are on top, kilograms on bottom. I'm just going to slide that right down there. And then we're now in moles. But I want mass. To find mass for moles, we got to do it from a mass. Calcium chlorine, 111 grams is 1 mole. Plug it in, multiply through, use your handy dandy Jordan calculator. So take 500.0 times 26, oops, wrong number there, 26.382 times 111 equal, divide by 1,000 equal, and I have what, 4 sig figs, 5 sig figs, so I should have 4 sig figs. So I end up with 1,464 grams. That's massive. How do we get that in there? We're going to probably talk about a supersaturated state. We're going to heat it really up high and then cool it down slowly. That's how they make those kind of solutions work. All right, let's try this one on your own. Pause the video, see what we end up with, how it goes. All right, pause it, try it. Okay, hopefully this wasn't too bad. Here's what we got. We're going to find the molality first, and this one's even bigger. It's 37.45254 molal. Again, that's a concentration, so we use it as a unit converter. We're going from milliliters of water, so we're going to have to use the density there. Doing the same process at using calcium chloride again. Answer this time is 10,654 grams of calcium chloride. All right, that's it. Hopefully that wasn't too bad. Again, I'm not going to test on it. I just want you to see it, so that way you have some background. All right, take care. Be good.